Welcome to the Toronto Geometry Colloquium, Season 2. This is a weekly web series all about geometry processing. In this colloquium, we aim at promoting young researchers and researchers from traditionally underrepresented communities. Every week, we'll have an opener talking about their cutting-edge research for 10 minutes, followed by a headliner giving us a keynote-style presentation.
And today's show is going to be a visual feast for everyone. Our opener, Zahra Montazeri, is going to talk about a practical poly-based appearance model for woven fabrics. And our headliner, Professor Theodore Kim, will talk about energy eigen systems and metabolic bunnies. And as usual, if you have any questions, and please leave comments in the YouTube live chat or our Discord channel. So first, it is my great pleasure to introduce our opener, Zahra. So she is a PhD student at UC Irvine, supervised by Professor Shuang Zhao. And before that, she obtained her master degrees at the same institute and her bachelor degrees in Sharif University of Technology in Iran. And the unique thing about Zahra is that she's not just like a talented graphics researcher, she's also a brilliant artist. So I strongly encourage you all to visit her website to see all of her great artworks. So back to her research, and typically in graphics, we care more about whether the results are visually plausible, but sometimes those results do not correspond to the true behavior in reality. But the difference is that Zahra's research actually brings the actual physics to those like models to model the behavior or rendering of the cloth. So actually the result she simulated correspond to the actual behavior of the cloth in reality. And today I'm super excited to hear an example of that in cloth rendering. So please join me to welcome Zahra.
Thank you so much for the great introduction. It's my honor to be here, and I'm excited to show our recent paper about cloth rendering. So if you may, I'll share my screen and jump into the presentation. So this is a paper that presented last year at SIGGRAPH, so I'm using the same slides, about a practical ply-based appearance modeling for woven fabric. This was a collaboration with Keyshot, which is Laxian. They're located in Denmark, and a collaboration with Professor Henrik Jensen. All right. So first of all, cloth rendering is very useful in daily life because it's because of all its application in entertainment and online retail and textile design. So virtually generating them is very important. But traditionally, all the cloth has been modeled as a 2D sheet. So it was like a mesh. And there are pros and cons for both. They are very lightweight, so they're very easy and fast to be rendered and generated. They're very good for macro scale models, but the problem comes in when you go to zoom in view. And in that case, it would lack the details, and it also doesn't handle the reflection of the transmission of light. So what if we have a lampshade and the light is coming from the back? Those are the limitations of the previous works. So there are also a bunch of other works, micro appearance models that are on the other side, very detailed. They are modeled in fiber level. They're good for close-up views and all the details are there. But the problems on the other side is that they are super heavy and they're usually hard to edit and they are just not practical. Then we have a middle ground approach. It's a balanced model that we have here to work in ply level, which I'm going to talk about how does that work. And the second contribution here we have is that we also capture the transmission of light. So if the light is coming from the back side, we can capture it accurately. Here is the preview that I just wanted to show real quick, that the light is going around. How does the reflection and the transmission of light shows up? And that's it. So here a quick background about the textile hierarchy. First of all, every cloth has been made from different yarns. like this, as we see here on the left. And then every yarn is combined of coupled plies, and every ply has been consistent of hundreds of fibers. So if you want to make something accurate, it has to be in fibers, but it's not practical. So in this model, we start with yarn level, which is conventional way of modeling the cloth, other than surface base, of course. But if you want to do a yarn level representation, it would be the one at the left. We have a yarn representation of a cloth. And then in second, we have the B, which is the ply curves. So that's the middle ground. And then C is the adding the fiber details. So all the fibers would show up on the surface of the ply. So instead of actually having all the individual fibers, we add the fibers as a texture on the surface of the plies. So in that case, the geometry become way lighter, because we don't have all the curves, but we only have the texture. So it would be visually appealing, but it's quite fast, and we call it interactive. And on the appearance side, I wanted to show how as a BSDF works, because we have a novel light interaction for the ply-based model. So here in this circle, actually, I'm showing a cross section of a ply. So there is a ply, and there are all these fibers passing through it. So as you see, all the smaller circles are the cross sections of fibers, and the entire circle is the ply. So we don't have anything inside the ply, because again, I said that we have a ply and then we add the fibers as a texture around it. So basically these circles inside are virtual. We don't have them, but we do want them to come up to compute a BSDF. So let's say for the story of the light interaction, light hits the point at the surface of the ply, the green arrow, and then part of the energy will be reflected back as a specular energy, which is the reflection, which is the regular microfacet model. And then part of it would transmit it through. It has a lot of inner transactions between all the fibers, and all the way to the back side, or to the opposite side of the ply when it leaves the medium. In that side, we again have another component which captures specular transmission. In that case, that would be the highlights that appears on the back side of the cloth. And then there would be another component, which we call it body reflection. We call it body because it comes from the subscattering part of the energy that has been captured inside the ply, and it escaped from the front side of the ply. And the rest of the body part escaped from the opposite side of the opposite side of the ply. So these four components form the entire BSDF of our model. Every time it hit the model, it would be four components that the energy would leave the medium from. So this is the BSDF that works for our ply level cloth model. And here I want to show the rendered result for each component. On the right, we see each component, what contribution they bring to the specular reflection, the specular transmission. As you see, they are mostly they don't carry color, and they are mostly for the highlights. And the body reflection and body transmission, those are the ones that carry the color, and they make the subscattering appearance for the full cloth. And on the left, we see the combination of all of them. All right, here is a demo I wanted to show, because we call this real time, which is quite fast, and the artists were like super excited about it. So I wanted to have a live demo to show how we can change the pattern. So here is a woven. You can change the woven pattern. You can change the width of the yarns. And then here is the backlighting. You see is vertically, and now it's horizontally. Ta-da! It's because of the yarn arrangement. If you have a satin, if it aligns vertically, it would transmit the light differently from if it's aligned vertically. So that's the very important aspect of an underlying geometry and how the geometry would affect the appearance. And this is a close-up to see all the fibers, all the yarns, everything. All right, so so I'm going quickly over some results. First of all, this is the microscale results that we captured under the microscope, and on the bottom they are the photographs, and on the top we see the rendered one. So we can manually tweak the geometry level parameters under the microscope, the number of plies, the geometry of the pattern and whatnot. Then once we have everything under the microscope, set up the color and everything, then we can move on for the for the top view. So this is a macro scale one. Again, on the left, we see the photograph compared to ours, the rendering. And we see on the bottom that actually the top one is the front lighting. So it's a piece of cloth, and then we lit it from the front. And the bottom one is lit from the back. So it's interesting, again, as I show you in the lampshade, that when you have a light in the back of the cloth, based on the geometry of the pattern of the cloth, it would be a very anisotropic highlight that would show up from the other side. So this horizontal highlight that we see that comes from the light in the back could be captured with our model that was not new compared to previous models. And on the right side, the 3 columns on the right is about comparison with the existing VCSDF model, because on the VCSDF model, it's not only much more expensive because they model it all the way to the fibers, while ours is on ply level. And also they don't have the reflection and transmission simultaneously to be captured. So we can fit the front side, we can fit the back side, and we can fit, if we want to fit both, which is the column that I marked, fit both, it would we fail for fitting both of them at the same time. So that was an evaluation with existing models. Then these are some more examples, again, with the same scenario, front lighting, back lighting with other examples. And again, the lamp model that I showed in the video, I just wanted to have a quick note here that the satin has a vertical reflection, and this one has a horizontal reflection in the back based on the pattern. And this is a video that I may skip for the sake of the time. Anyway, let's see it. It's a couple seconds. And this is a zooming view. So the limitation, first of all, this is for woven. Now we have the knit fabrics as well, so we are publishing it soon. And there's another work that we want to continue is the multi-resolution. So it can be not only for the ply level, but we can also transfer it all the way to the surface. And again, non-circular cross-section, which is a very common limitation for all the fiber level representation for the cloth. And the conclusion, appearance model for woven fabrics, that's what we proposed. And then we have the reflection and transmission. And lastly, it's quite fast and interactive. And I want to thank the reviewer and also the artist of the company whom I was collaborating with for generating the models and whatnot. Yeah, that was it. Thank you. So should I stop screening here?
Yeah, you can stop screen sharing. Yeah, thank you for this great presentation. But people are super excited about the demo you show. Like, people just ask, is the demo available online?
Yeah, they can. It is already released. So it is Keyshot 10. which is released last year, and the main feature was having the cloth. So it's already there, but the video that I showed is also available on my website with the presentation that I showed. But they can also download Keyshot, actually buy it, and then they can just quickly play with it as it is. Yeah.
Okay, thank you. And then we will proceed to the talk about headliner, and we will also have a joint Q&A at the end.
Sure.
So okay, so now it is my great honor to introduce our headliner, Professor Theodore Kim. He's an associate professor at Yale University, and before that, he's a research scientist, a senior research scientist at Pixar. And in graphics, he's a person that does not need an introduction. Many of his work on simulation has been using many Pixar movies, and his massive contribution also made him a recipient of the Oscar Scientific and Technical Awards in 2012. And in addition to his research, he's also a very great educator. Like his SIGGRAPH course on dynamic deformables has one of the best SIGGRAPH courses I have ever seen, and it contains many deep understanding of many methods, and also the source code is available. And personally, I'm also benefit a lot from the note on how to prepare a talk posted on his website. Personally, I'm still following his guideline to prepare my own talks. So, and there are just too many great things to talk about, like Professor Kim, but I don't want to steal too much of his time. So without further ado, please join me to welcome Professor Theodore Kim.
Oh, thank you, Derek, for that lovely introduction. Oh, and thank you, Zahra, for a fascinating presentation, actually. I have many questions. All right, so let's get started. Okay, so today's episode, everyone can see my screen okay, I hope? All right, so
yes.
Today's episode, I'm actually going to break into 2 episodes. So it's energy eigensystems and Mandelbrot bunnies. So this is actually 2 separate talks. All right, so let's get started on the first one. All right, so let's look at energy eigensystems. All right, so this is actually going to be our paper from 2019 that we presented at SIGGRAPH. This is with my collaborators Brendan Smith and Fernando de Gos. So let's start off with just a shot from when some of this algorithm is actually used. So this is a shot from Cars 3. So this is a prank. So they're going to inflate the tires of this car to be really big. And this is a physical simulation. So everything is going to squash and stretch in a physical way. But of course, there's lots of interesting geometry going on too. All right. Oh, and it's a gag. Oh no, his tires are big. Okay. And it's all a simulation. All right, so people have been doing these kinds of simulations in computer graphics for a long time, actually, so about 30 years. So the weird thing is that there's a real big mystery sitting at the middle of all this stuff for the last 20 years or so. All right, so the elastic response of an object, you can write it down in terms of some sort of elastic potential energy, and there's no one right energy, actually. So you pick which energy works best for your application. It does look a little bit scary. There's a lot of different energies out there, but if you look at them a little closely, they actually do have a shared structure. So I'm highlighting them here. These are called the deformation invariants. These are the basic building blocks for elastic energies. And this has basically been the theoretical tool that people have used for about 70 years to analyze these kinds of deformations. All right, here, so I've shown, here are the actual expressions themselves. So I'll go into their meaning a little bit later, but the point is that they've been used in one form or another for a long time. So at least from Mooney back in 1940. All right, so if we go to like the 90s or the 2000s, it seems like we're on easy street here with computer graphics. So we have all this awesome mechanics work that we can just pull from. So let's just use some of that stuff, right? And then we can do simulations. Here's one of the simplest energies you can have. This is STVK, Saint Venant Kirchhoff. All right, and you can see those invariants that I said before. Yeah, we built this energy out of those. All right, so let's see what happens when we try to simulate something with this energy. All right, so we have a square of material here, and we're going to grab it by the red nodes, and we're going to stretch it out. All right, looks okay, right? So maybe we can go along with this. Let's try the opposite. All right, we're going to try compressing that square. All right, and really weird stuff happens, actually. So it's actually difficult to even visually parse what the heck just happened. The thing to take away from this is this isn't quite going to work. All right, we need to do a little bit better than this. That's okay, right? So I said there's tons of energies you can pick from. Let's just pick a different one. So we can pick, say, this one. This is called a neo-Hookean energy. You could try this. I'd argue that the results are actually even worse. So what happens is it creates a nearly infinite force under compression in the wrong configurations, and the whole thing just explodes. So at that point, there's nothing to even show. The whole thing went to infinity. All right, so people tried out a lot of these energies early on in computer graphics, and a lot of them don't really work, or they don't work that great. All right, so the one that people converged on was this one. All right, so about 2002, they started using what they called stiffness warping or co-rotational energy or rotated linear energy. Lots of people discovered this around the same time, and these are all the same energy actually. I would argue that this paper from 2002, this is the one that really first posed it to computer graphics. All right, so let's see what happens when we use this energy. All right, let's do the same thing. Let's stretch it out. Looks pretty good, right? And all right, let's do the other one. Let's compress it. That's where STVK fell down, right? All right, we'll compress it, and it does okay. All right, so it doesn't do the weird thing that STVK did. So this is a reasonable response. And so for that reason, this has been the standard in visual effects for a very long time. So a lot of movies, like all the Planet of the Apes movies, or Moana, or Finding Dory, even at Pixar, this was the elastic energy that people used. All right, so I said there was a mystery with this whole thing. So if we look at this energy and the terms that make it up, it looks different from all the other ones than that big stack of energies that I showed you before. And this is not just a cosmetic difference, actually. There's not one easy change of variables that will get us from the energy on the left to something that looks like what's on the right. All right, so the main thing is that, yeah, I said that there's these invariants. These are the basic building blocks for all these elastic energies. And the weird thing is this co-rotational energy, the one that everyone uses, you can't actually write it down in terms of these supposedly fundamental invariants. All right, so this is a little troubling. So how fundamental can these invariants be if they don't actually capture the thing that everyone actually uses? Okay, so at this point you could say, who cares? There's an energy that everyone uses, it works well, so what does it matter that it doesn't fit into whatever theoretical framework? So if you start working with this model, things can go weirdly off the rails. Okay, so McAdams at UCLA, they looked into this in 2011, and here you stretch it out, and you can see these weird instabilities start to occur. So this is what they found, and something's missing, right? So some piece of understanding is missing here. So since there's no there's no existing theory to analyze these energies, a bunch of research groups over the last 15 years or so, they kept finding that there were these subtle, non-obvious terms that seem to appear during implementation that have implications in simulation stability. And actually, over the last 10 years, there were at least 3 groups that took a stab at figuring out what the heck is wrong with this thing. So there's this the paper from Caltech, there's one from UCLA, and there's one from USC. All right, and credit goes where credit is due. So for example, at UCLA, they did figure out what is missing here, and they were able to stabilize the simulation. So you can see here that yes, back in 2011 at UCLA, they were able to stabilize this thing. Well, we're still left with the same question though, which is, all right, so we have these supposedly fundamental invariants. What went wrong? Why were they not able to actually express this energy that everyone actually uses? And then there's a follow-up question to this, which is, okay, so is there a piece of missing theory here that makes all this insufficient? Okay, so I'm just going to go ahead and ruin the mystery here. All right, so here are the answers. So the problem with the fundamental invariance is it's actually the wrong invariance. All right, and to answer the second question, what do you miss because the previous theory was actually missing something? And I'm going to argue that if you use a new set of invariants, it actually reveals some very interesting structures that were very hard to see from the previous perspective. Okay, so to begin to see why these current supposedly fundamental invariants are actually not sufficient, we're going to need a little common language to parse with. So the thing to glom onto here is F. All right, so F appears in everything. So let's look at what F means, and then that'll give us a toehold into interpreting the rest. All right, so what is F? This is called the deformation gradient. So this is a geometry symposium. Perhaps this is review for some of you. If not, we'll do a little refresher. All right, so say we have an undeformed tetrahedron here. What F does is it will encode how it rotates and stretches when you deform it. All right, it doesn't do translation. That part's been factored off. All it does is it'll encode a rotation and stretching that has occurred. All right, so again, F is the deformation gradient. What does it mean? It means how much did I rotate and scale my tetrahedron? All right, so rotation and scaling, unfortunately, have been they've been entangled here. We'd like to separate the two. So the Swiss Army knife of numerical analysis is SVD, singular value decomposition. So let's take the SVD of F, and then we can see if we can disentangle these two things. So I've expanded the middle term here, the scaling matrix, into the sigmas for the 3D case, and these are actually the things that we care about. So we'll be able to interpret F very cleanly based on these. All right, so these singular values, these sigmas, they have very intuitive interpretations. So each of them, we have this cube of volume here. We can think of each of these as the length of the edges on the cube. All right, so the first singular value is just the length of this side, and the second one is the length of, say, the z coordinate, and the third one is the length in the y direction, that sort of thing. All right, and then if we look at our first deformation invariant, it's actually the squared sum of these three. So it took the lengths of the cube and squared them, and it added them together. All right, so it's just the summed squared lengths. Okay, if we look at the second invariant, it actually bumps it up a dimension. So instead of lengths, it actually looks at areas. All right, so it actually is the area of this face, the area of this face, and the area of this face. All right, and if we look at the third invariant, it's actually the volume of the entire thing. Okay, so from this, I think it's pretty clear why these three invariants have been considered the fundamental invariants for such a long time. If you're going to characterize how something is deformed, you look at its lengths, its areas, and its volumes, right? These are three excellent ways to measure things. So it seems like these should be sufficient, right? So what went wrong? All right, so again, here's this energy that we've been looking at that everyone actually uses, and it doesn't fit within these invariants. All right, so here we'll do a little more geometry processing-y stuff. We're going to cut off that second term, and if we do that, we get the ARAP term, the as rigid as possible energy. So this is very popular in geometry processing, so let's look at it here. Okay, we can do a little bit of rearranging, and that actually turns into this instead. And something friendly appears at least. Okay, so we did some manipulation, and okay, one of the fundamental invariants appeared. But what's this? Right, trace of S. This is actually the troubling term. So this is irreducible. It will not yield. It will not be written in terms of fundamental invariance. What the heck is it? All right, so let's make a little more space for ourselves. So S, this is actually from the polar decomposition of the deformation gradient. So this is an alternate way of separating stretch and rotation, and S is stretch and R is rotation. So if we look at the trace of S, it actually corresponds to the unsquared sum of lengths on that infinitesimal cube. And the problem is that the closest thing we have to this with our supposedly fundamental invariance is the squared sum of the singular values. And you can't express the unsquared sums of three things using the squared sums of three things. So that is one of the pieces of the mystery here. Why can't you write the corrotational energy using these fundamental invariants? Because you can't write unsquared stuff in terms of squared stuff. All right, so these three invariants are clearly not enough. So what are we going to do? All right, let's look at the first one, and I'm going to do something that looks extremely careless here. I assure you that something a little more concrete happens in the paper. Let's just say, well, all right, F transpose F, let's just replace it with S. All right, then we'll get that thing that was irreducible and wasn't showing up in our energy before. And let's just keep doing this. All right, let's do it with the other two as well. So anytime we see FTF, we're just going to replace it with S. It's fine. It's fine. All right, again, we give a better reason for this in the paper. All right, if we have these three invariants instead, then suddenly the ARAP energy can be written in terms of invariants. All right, so we can show that this new set of fundamental invariants, they actually express exactly the same things as the old ones, but it actually adds quite a bit more. Okay, one thing I didn't mention to you before is that there's a whole bunch of energies in geometry processing that can't be written in terms of these supposedly fundamental invariants. But if we use these new invariants that I just proposed, it actually yields instantly. So you can actually start writing all of these in terms of these new set of fundamental invariants. Okay, so that goes back to our first mystery here. So why can't the fundamental invariants express this? It's because actually they were insufficient. They're the wrong invariants. They were close, but we had to do a little something else. All right, so we have a more detailed answer. Don't use the stuff on the left, right? I know it's a little scary. They're 70 years old, but doesn't necessarily mean you should always trust them. So use our invariants. So they can do everything that the old ones could do, and they can do a little bit more. All right, and if you don't believe me, you can read our paper. All right, so on to the second question. Why does this all matter? So what did we miss because the theory was insufficient before? What we're going to see is that there are eigenstructures that you can now see because we have the correct set of invariants. And to this, you might say, what eigenstructure? What are you talking about? All right, so eigendecompositions, this is something that it's pretty well understood. And maybe you've seen it in linear algebra class. All right, eigenstructure is a little bit more difficult to see because it's the decomposition of a higher order tensor. All right, what are you talking about? What tensor? All right, so this is the energies that we've been using so far, right? So energies are just scalars. And if you actually want to use this in some sort of geometry processing or simulator, you will need forces, right? So you take a derivative of this, and then there's a standard transformation to get from this 3x3 matrix to a bunch of forces, right? And you can use those to write a simulation. So if you're using a implicit solver, which is what Pixar uses and what a lot of places use, you're going to need another derivative. So the second derivative here. So this is a rank 4 tensor, unfortunately. Okay, so if you actually write down the rank 4 tensor, it looks like this. All right, so it's a matrix of matrices, and people are not used to having to manipulate stuff like this. And frankly, it kind of hurts to look at this, doesn't it? And the trick here is usually, all right, we're not going to work with a rank 4 matrix. We're going to flatten it into a matrix. So we can do that here. Still kind of hurts to look at, right? And still kind of clear as mud. So at least we have a matrix here. We're more familiar with matrices, so at least we can just throw it down MATLAB, right? So if we want to know what the eigenstructure of this is, we can throw it down MATLAB, and we'll start with a sea of numbers. We'll take the eigendecomposition, and we'll end up with another sea of numbers. So I'm going to argue that you shouldn't do this, actually. Sometimes there's a structure that you'll miss out on. So we can actually find eigenmatrices for this energy instead. So what's an eigenmatrix? So here's our usual eigenvalue problem, right? So you have a matrix on the left, so it goes matrix, vector, vector, right? AXX. This is your usual eigenvector problem. So here's a slightly less familiar version of that. So if you have a 4th order tensor, you can do the exact same thing, actually. So instead it's tensor matrix matrix, but it's the exact same thing. It's actually equivalent to the eigenvalue problem. And in this case, instead of an eigenvector, we have an eigenmatrix. Now, the thing about the eigenmatrices of these tensors is they actually have a super simple structure, all right? So we can actually look at the first eigenvector of this equation. It actually is this, all right? So what are U and V here? I see there's a constant matrix. What are U and V? We had the SVD of F from before. It's actually the U and V from the SVD of F. So actually the first eigenmatrix is constant in the SVD of F. It's a constant. All right, we can look at the second eigenmatrix. It actually has this form. So you can see that actually just all that happened is the constant matrix in the middle changed a little bit. And we can keep going, and you can get 6 eigenmatrices like this. So we can show that these are the 6 eigenmatrices of any energy that you can write down. So all of those energies I showed you before, these are the 6 eigenmatrices of them deep down inside. So the structure is quite simple, right? They're constant in the SVD of F. And if you're lucky, actually, there's supposed to be 9 eigenvectors. If you're lucky, these are the last 3 eigenvectors. All right, so for example, the ARAP energy I showed before, these are the eigenmatrices, all right? So there's really no excuse to ever having to take the eigendecomposition to that 9x9 matrix ever again. We actually know what the eigenvectors are every single time. All right, so you can use this to actually find analytic eigenvalues. So if you want to know what the full eigenstructure of an ARAP energy is in any tetrahedron, it's this, right? Is this every time. We have it in closed form. All right, so no more numerical 9×9 eigen decompositions of the Hessian. You can just write this down directly. Okay, so for example, I showed those 3 papers from before, and I said, yeah, so something was a little bit missing. So they went through a lot of work to figure out what was the missing piece. And if you go through these, it turns out the missing piece was if you don't have the right invariance in place, it's really easy to drop these 3 eigenpairs on the ground. But we do have the right invariance in place now. So when you go through with this derivation, they just pop out automatically. All right, and this actually translates into some pretty sweet code. So on the left, this is all the stuff that we had to do in order to get the Hessian of the ARAP energy originally. And once we know what the eigenstructure is, it compresses down to the code you see on the right. So it's smaller and it's faster and it's just plain better. We don't really see a reason not to use this thing. And from a theoretical standpoint, you can see the exact moment when these energies become indefinite, which is really interesting. It's really hard to get definitive expressions for eigensystems sometimes, but we got them, right? And we can see the exact moment when this stuff just becomes non-convex. So, before you have this, there are speculations. We see this paper on the bottom here where maybe it's convex, maybe it's not convex. No, we have it dead to rights. Definitely not convex. We can tell exactly when it becomes non-convex. All right, so that was a lot of math. So let's watch another movie. All right, here's a scene from Bao. We actually used our formulation of the ARAP energy for the body of the mom here. Let's see her crawl over the table. All right, we used it for her body, and that was then used to clean up the clothing simulation. All right, so I said there's 2 episodes. I'm going to summarize the first episode. All right, don't use the invariance on the left, use the invariance on the right. It'll be fine, trust me. All right, and if you ever find yourself with a 4th order tensor, maybe don't flatten it right off. There might be a really interesting eigenmatrix hiding in there. All right, and if there is, maybe you'll be able to find some fast, compact, and robust code. Okay, that's the end of episode 1. Give me 1 second while I switch to my next slide deck. All right, so we were at energy eigensystems before, and now for a change of pace, let's look at some Mandelbrot bunnies. Okay, so I'm going to talk about this paper I published at SGP back a few years ago. This is Quaternion Julia set shape optimization. So as I said, this is a totally different topic. I'm going to ask a question. Can we find a Julia set in the shape of a bunny? So you might not know what a Julia set is. That's fine. We'll go over it in a second. But the answer to this is yes, and here is the Julia set. All right, and this is a rational function. So this is a shape that was generated out of a rational function. All right, it's not our traditional, just something that you modeled by hand. Okay, let's back up a second. What's a Julia set? All right, so hopefully you've seen this before. This is the Mandelbrot set. This is probably one of the most famous structures in all of math, right? This was discovered by Benoit Mandelbrot in 1980. So a Julia set is something that is slightly different from this. With one tiny little tweak to the computation, you can get all these other shapes as well, right? So it's similar to the Mandelbrot set, but there's a whole family of different shapes, right? So these were studied back in 1917, 1918. The 3D version of this was actually published originally at SIGGRAPH, right? This was Alan Norton back in 1982. People were asking, what's the 3D version of this? And he showed that there's no 3D version. You actually need quaternions. So there's a 4D version of this. And then you take a slice out of the 4D volume to see what it looks like in 3D. That was back in the 80s. There hasn't really been that much work on this since then. The most recent one, this is called the Mandelbulb. I think this was like introduced in like a blog post or something like that. It wasn't at SIGGRAPH or anything like that back in 2009. That being said, people are still interested because it makes really cool shapes. So this thing shows up in a lot of movies. So if you look at Doctor Strange or Annihilation or Big Hero 6, there's a bunch of really dramatic scenes where they actually use this, the Mandelbulb. Right. Past this though, no one's really using this style of geometry anywhere in graphics. And I think the reason for this is unless you need something that looks either exactly like the Mandelbulb or exactly like the Mandelbrot set, it's not clear what you should do. So I want something that looks fractally, that doesn't look exactly like the Mandelbrot set. What am I supposed to do here? And it hasn't been that clear that you can actually do anything for a while. Until my colleague Catherine Lindsay, she published this paper back in 2014. So in the 2D plane, at least, she showed, oh, actually, you can generate any Julia set that you want in any shape that you want. So you see here that she generated a Julia set in the shape of a kitty or in the shape of a butterfly. And I was really excited when I saw this paper. And so I emailed her and I said, do you think this generalizes to quaternions? And it turns out this stuff uses like really heavy machinery from complex analysis. So it was not clear at all that it would generalize into quaternions from just the complex plane. So that was a little crestfallen by that. But then I said, okay, so let's write an optimization or something instead. So we don't have an analytic approach. Let's throw a numerical approach at it. All right, so let's go through it. What is the numerical approach? Okay, so how do you compute a Julia set? If you've never done this before, it's pretty simple and it's a lot of fun. So let's do a quick run through. And if you haven't done this in a while, it'd be a nice refresher. All right, so we're in the complex plane. And let's look at just one point in the complex plane. We're going to push it through a map. So this is the canonical map. So we're just going to take that point, we're going to square it, and then we're going to add some constant c to it. All right, when we do that, then it just iterates, right? So it moves that point somewhere else. We'll just do this over and over with the next point, and it'll go here. The next point will go here. And we do this over and over, and we get an orbit, right? So it just has some trajectory through space. And a lot of the times what happens is it'll just blast off to infinity. A lot of the points do this, all right? So you can actually tell if it's going to blast off to infinity using a bunch of theorems. So for example, there's some theorem that says, okay, so if this orbit ever goes outside of a circle of radius 2, then we have some theorems that say that, yes, it will always blast off to infinity. All right, so if we do this for every point, every pixel in our screen, and we color them black and white, so the black ones say, these are the ones that did not blast off to infinity, and the white ones are the ones that did blast off to infinity, then you get these really wild shapes. All right, and as I said, people were looking at this back in the 1910s, and if you change C, so just the one on the right here, then you dramatically alter what shape that you actually get. All right, so if you never coded this up, it's really easy actually, and it's a lot of fun. So I highly encourage you to try it. All right, so the 3D version of this, you just do the exact same thing, but with quaternions, and you can see you can just take slices out of the quaternion, and you get these stretched out shapes. All right, these are just slices. I then ran marching cubes on this, and you can get a shape like this. So it looks like, you know, some sort of pulled up taffy or something like that. Okay, we still have the control problem. So this is great if you want something that looks exactly like that Julia set. There actually are not that many degrees of freedom here. So 2D, you only have 2 degrees of freedom that you can play with. And in 4D, you only have 5 degrees of freedom that you can play with. So if within those degrees of freedom, you can't actually find your bunny or the shape that you want, you're pretty much out of luck. And this is the function that everyone's been experimenting with for a long time. All right, so I was looking at this and I said, all right, well, are there other functions that we could try that maybe give a little bit more control? All right, and the one I arrived at was this one. All right, so instead of a quadratic, why don't we use some arbitrary rational function here, where we're going to stack as many degrees of freedom as we want into the thing. So this factored polynomial here, this has a lot of attractive properties. Right, so for example, the top polynomial here, these t's, these are just fixed positions in space. Depending on where you decide to pin these become attractors for the Julia set. Right, so we have these red points here, and if you scrub them around, these are the positions of T. And although the whole shape changes pretty drastically, you can see it's following it, right? And all the red points, they are always on the interior of the Julia set. So it's an attractor for the Julia set. If we look at the bottom here, these points, these are repulsors. All right, so let's do the same thing here. This blue point on top, this is a repulsor, and you're going to see the Julia set, it does everything it can to stay out of the way of this repulsor. All right, one last feature of this rational function. We raise everything to a power. So by adjusting the power, you can literally adjust the power of attraction and repulsion for each of these roots. So for example, in the middle here, we have power equals 1. And as we pump up the power of the middle root, it becomes more and more dominant, and it is more and more on the interior of the Julia set. All right, so that's the formulation. We have a bunch of attractors, a bunch of repulsors, and we have a way to tune their power. All right, how can we use this to do an optimization? How can we get the computer to actually find a shape for us? All right, so let's start with a simple shape. I tried a bunch of different ways to do this optimization. All of them blew up spectacularly, actually. But let's try out for, say, a tooth. I'm going to show you the one optimization that actually did work. So we want to be able to characterize whether or not a certain Julia set is actually pretty close or pretty far from the shape that we care about. So what we're going to do is we're going to take the sign distance field of the shape. You see it on the left here. And we're going to try to match it against the potential field of the Julia set. So there's a known way to compute this. So you take the magnitude of the rational function at each point, you take the log of it, and it actually will give you a potential field. All right, so if we take the inner product of these two, then we can say, okay, so if these two match, then we'll get a certain score. And if they like mismatch really badly, we'll get a different score. All right, so in this case, if they match, we'll get something that is a really big negative number. All right, and if they don't match, then we're going to get small negative numbers or positive numbers. In fact, we can normalize this. So then if they match perfectly, then we'll get a score of -1. All right, so now the game is, let's just drive all this to -1. All right, now we have to pick the actual variables that we're going to optimize, and that is the stuff in the rational function. And there's an obvious thing to pick here, which is the root positions. And I tried this. I couldn't get it to work, actually. It doesn't work very well. So what happens is that the optimizer thinks that it's a really great idea to just push those roots off to infinity, and then it seems to think that it's doing great. All right, so that just didn't work at all. And there's also another problem here, which is, what if I actually didn't give it enough roots to work with? How do I know, right? How do I actually add roots to this optimization? This is a discrete event, and we want a continuous optimization, so this is not a good idea. All right, so instead I decided, okay, this is too hard. I failed too many times. Let's break this problem into two problems. So instead, I'm not going to hand root placement to the optimization. I'm going to give the root placement as an initial guess. All right, and then once we have this initial guess in hand, the optimizer is only going to get to tune the powers of this rational function. All right, so then how do I get an initial guess? I tried a lot of things here. Again, here's all the failures. I tried tons of different things and they all failed. So then I went back to my colleague Catherine Lindsay's paper, and I actually bugged her to send me the root positions of the polynomial that she was using. And here they are for the kitty cat. And you can see they're all on the surface, right? So that suggests maybe it's a really good idea to put all the roots on the surface. And there's actually some evidence that they're distributed along the surface according to some like Laplacian potential. So it's like random walks from infinity. That explains the density of points along the surface of the kitty. All right, so we can use this to come up with some approximation. So this is just an exterior radiation problem with a Sommerfeld condition, and it just solves the Laplace's equation everywhere. This is sort of the intro to boundary element method problem that everyone solves with their BEM library. So I downloaded a BEM library and I got this to work. So we can see the potential field, for example, for like a bunny or a frog right here. And this is still not exactly what we need. So we still need to convert this into a bunch of root locations. And for this, I just leaned on a paper that I had published a few years before that. This is the third one here, cubature approximation. This has been known for a while, actually. So it goes under a whole bunch of different names. So in the whole compressive sensing literature, it's called stuff like orthogonal matching pursuit, that sort of thing. So the important thing is that we can use this to come up with a bunch of point sources that then approximate the potential field. All right, so that's what we got here. So out of a cubature approximation, we got a bunch of point sources. In red, you can see negative weights, and in blue, you can see positive weights that then characterize a potential field. but you can see that the negative weights, they're kind of in these concave regions. Like it says, like, Julia said, don't come here, go away. And the positive weights are in convex regions saying, Julia said, come towards me, we want your shape here. And we can go ahead and we can just plug these in as an initial guess into our rational. So you can take the position and plug it into T, and then you can take the weight that the cubature optimizer found and plug it into the power. And we can do the same thing for the negative roots as well. So if this all sounds pretty ramshackle and ad hoc, that's because it absolutely is. I just tried tons of stuff, and this is the first thing that I tried that actually worked. If you have a better idea, I would love to hear it, because this is a pretty difficult pipeline to work with, and I would love to see something more elegant here. All right, actually we're done. So now I'm just going to show you tons of results. All right, here is what we found for the tooth, the potential field for the tooth. And then we ran it through the optimizer, and here we go. All right, so we used a BFGS to optimize here. And if you've done like neural net optimization, you have to kick it with a bunch of different regularization terms or what have you. And that's what we did here. And you can refine this with more Julia set iterations, and you get interesting shapes like this. You can start playing with this actually. Lots of weird stuff happens. So you can start picking different slices in Quaternion space, and then you can see it sort of teleport in and out of reality this way. You can start moving the roots backwards and forwards in space. You can see that it sort of tears itself apart. But the really interesting one is when you just translate the sucker in space, it like sort of sparsifies. And then you can look for really interesting like rotted wood type shapes that are generated by these. Okay, next up is the bunny again. All right, so here is the root locations that the cubature optimizer found. And here's one of the shapes that it found during the optimization. Kind of looks like like a bunny covered in cake frosting or something like that. If you keep running the optimizer even longer, then it gets an even tighter fit like this. All right, and we can play the same games, so we can have it teleport in and out by picking different slices in the Quaternion space. And by translating it, we can again find that hollowed out bunny that I showed up at the front actually. All right, last one is the frog. All right, here is the root locations that we found. Here is midway through the optimization, one of the frogs that it found. And if you keep going, you get an even tighter fit to the frog. Again, this is a Julia set. All right, and if you play with this, you can find really interesting sort of driftwood type Julia set approximations to the frog that look like this. But the really wild part is actually when you look at the optimization itself and you see all the shapes that it actually passed through in order to find that final frog. So here it goes. So it actually turns out that the initial approximation was pretty rotten. So it's actually miraculous at all that it even found anything. But it does, and it does converge to the frog. As I said, as with any optimization, you have to kick it, and you'll see that it gets kicked in a second. Yep, there it went. All right, and then it locks onto the frog. And this stuff takes a while. So if you're lucky, it takes an hour to optimize. If you're unlucky, it takes a day or 2 days to actually find these shapes. And here are the fitting errors. As I said, you have to kick it with various regularization terms. There's more details in the paper. You can see it converges, and then it stalls, and I have to kick it. And here it is for the bunny. I had to kick it a few times. And here it is with the frog. All right, there's lots of limitations to this stuff. Initially, we had to compute the stuff in 80-bit precision because there's a big division by a giant polynomial. And as a result of this, if we try to do more complicated shapes, the optimization does stall out. So I tried to fit it to the armadillo. You see that here? It's not great, right? You can tell it's the armadillo, kind of. And then we tried it with the dragon, and it kind of looks like the dragon's like trapped in foam or something like that. It didn't really converge to the dragon. We published a paper last year that tries to solve some of the precision problems. It's still a very difficult problem. And the last thing I want to show you is one of the really great things about the Mandelbrot set is you zoom into the Mandelbrot set, and there's lots of tiny copies of the Mandelbrot set in there, right? So I think it's valid to ask, if you zoom into the Mandelbrot bunny, are there tons of little bunnies down there as well? All right, so we tried this out. I'm going to zoom into the bunny. We're going to zoom into the tip of its ear. This is pretty expensive to compute, actually. All right, we're going to keep zooming in to the tip of the ear. All right, still no bunnies. What's this thing right here? This little speck of dust. So if you zoom in there, it's not quite a bunny. It looks like it's ears though, doesn't it? Almost. And actually, according to my colleague, Professor Lindsay, there's an excellent chance, actually, it's almost certain there are copies of bunnies down there somewhere. It's just really expensive to explore. So that's for future work. All right, so just a summary. You can find a Julia set shaped like a bunny, but it's not easy. There's convergence issues, and to be honest, I haven't run this code like 6 years, so there's code rot issues at this point as well. All right, so maybe you can try to find a new shape. All right, so as you all know, unless you have really great collaborators, good work doesn't happen. So thanks to all my collaborators for helping me out with all this stuff. Otherwise, none of this would be possible. All right, and that's it. I'm gonna end with, this is usually how I end with questions on this slide, but I think we're gonna go back to just our faces. So I'm gonna stop sharing.
Yeah, thank you for the great talk, and also thank you, Zahra, for the talk. So we'll now start our joint Q&A session for both speakers. And in the meantime, if you have other questions, then please feel free to leave them in the YouTube live chat. So first, we'll let Professor Kim take a break. We'll start with a question for Zahra. So so in your in the video you showed about like the class simulation, is the simulation also done in the Young level, or is it actually the standard like surface class simulation and you just render using your approach?
Yeah, that's actually a very good question. The simulation are all in the cloth level, so they're all surface-based simulation. And then once we have the static final geometry, then we add the yarns and the fibers and everything on top of that. So that makes it quite efficient because the simulation is in the yarn level, in the surface.
I see. Probably a follow-up on that is it possible to, for example, do something like differentiable rendering for this like a multi-scale representation of the class? Basically, you can kind of for example, take an image of some class, then you can simultaneously optimize the geometry also, or the like detailed textures, basically optimize different levels at the same time.
Yeah, that would be a great future work. But we for now we did a for matching the photograph, we had a comparison with the inverse rendering, but we didn't use the differentiable rendering. But we had an inverse rendering problem with the pre-trained neural net VGG16, if you're familiar with, to find out the difference between the actual rendering and the parameters that we want to set with the appearance.
Okay, thank you. And next is a question for Professor Kim. So just about like the first part of your talk, like many people are tackling like the robustness issue in like simulation, and then even until like today, we're still hearing like people saying that like simulation is not robust, they have some issue or not. We're just curious, like in practice, how do the artists actually handle these things? Do that once they encounter like a simulation that may blow up?
Let's see. So unfortunately, a lot of what happens at Pixar is it blows up, and then they say like I have to like sculpt my way out of this. So they actually go through with sculpting tools and they just fix it. So if you have a good simulator, it's like, okay, so I don't have to do as much sculpting. But my impression has been, and I didn't have to do this myself, fortunately, that they just sculpt their way out of it.
I see, but once after we have your like the analytic eigen system and making right. Like
it doesn't do translation. That part's been factored off. Nope.
Pardon?
Sorry.
Oh, sorry. Yeah.
Okay.
That wasn't me. Yeah.
Okay.
It was like.
I'll restate my question. So okay. So like once we have your like approach, like those analytical expression of like the eigen systems, is it? Once we can also use that to kind of make our system from definite to like semi-definite so that it's more robust. Is there other robustness issue that still remains after this fix?
Collisions. So
collisions.
Yeah, so the material is nonlinear in a certain way. It's like you want the worst nonlinearity. It is a collision, right? It's a step function. It's the worst nonlinearity possible. So yeah, we haven't. I didn't talk about that at all, but yeah, it still really stinks.
I see. Thank you. And the next question is back to Zahra. So have you considered your representation can be extended to rendering other materials, for example, like rendering a human skin, which has a lot of like fine details on like the, I don't know how to call it, like the microstructure or something like that?
Yeah, actually that would be a great direction to take into, because all that what we are basically going through, it's the subscattering approximation. So anything that we want to have the subscattering like skin or hair, that would be kind of a inspiration. But the thing is that here we have the main contribution is that we have an aggregation model. So instead of a bundle of fibers, we now have a single cylinder as if it's aggregated the entire geometry. So for something like hair, if we can do a bundle of hair as if it's as a like a huge geometry, and then we capture the inner interactions within that, that would be a great acceleration in rendering process.
Yeah, I can see that if we can kind of have like a aggregate representation of like a bunch of small hairs into like a big hair, potentially it would be very cool. Thank you for that. And the next question is for Professor Kim. Like when looking at your like the second part of your presentation, those geometry are absolutely like amazing and beautiful. But we wonder, is there other application of that approach other than, for example, making artistic geometry?
Yeah, actually, I dropped that slide in the interest of time. People have looked at like heat exchangers and like radio antenna and stuff like that. So there's these things where there's these form factors. It's like, all right, we have to get something in here with the most surface area possible. So you could see we're years away from this, I think, but like you could see some tool where it's like, give me something in this shape with the most surface area possible, and this would be one way to discover it.
I see. Well, this is what a contradictory from a lot of people are looking at finding the minimal surface area, but you're looking at like the maximum surface area with this approach. I see. Oh, that's interesting. And another follow-up on that is that just imagine that because you generate such a complex geometry, like is there a better way to render that? Because I imagine like standard way to use like margin cube to create a mesh, but for those geometry will be like crazy high resolution mesh. I'm just curious how you render those things. Is there a better way to do that?
So far, yeah, we did the ugly thing, and it was just we marching cubes it, and then you get like billions of triangles or something like that. So this is why I had to ask Tom Duff to help me render it, because I can't render it myself. There may be ray marching ways to do this. So I think somebody I'm gonna mispronounce his name. Inigo Quiles, IQ. He's one of the guys who made Shader Toy. He put something online about like there might be like a ray marching way to do this where you actually trace the actual potential directly. I don't think he got the same geometry right out of the box, so there's a little bit more work that needs to be done there. But yeah, there might be a cool algorithm just waiting to be discovered there.
Okay, thank you for the answer. So yeah, so because we are already 5 minutes over, so if you have more questions, please feel free to post it in the Discord channel. Yeah, we will. I believe the speakers are here are very happy to like answer those questions offline in the Discord. So now let's thank you for our speakers again, and also thank you everyone for joining this colloquium. So this week, I also want to thank the artist Joy Richu for making this the poster for this week. And next week we are going to have Chenfangfu Zhang, Professor Chenfangfu Zhang, and then also the Sumuk Banzo. Sorry for not pronouncing correctly. So for our talk next week,